So the last session is now moving into kind of a high-tech and futuristic phase. Appropriately enough, we have the introducer is Margo Seltzer, who does computer science work, and I've collaborated with her on aspects of grid computing. So Margo.
So our first speaker is going to be Hiawatha Bray. He is the technology writer for the Boston Globe. He's been doing that for almost 20 years. He has a bachelor's in economics, a master's in communication, has a list of awards, including the most influential journalist covering technology, the John Hancock Award for business journalism, and more recently, he's authored a book called You Are Here, about the history and future of how we find ourselves. Now, when I introduce people, I always like to have a little tidbit that you couldn't find out from just Googling them. And so it turns out that we've been very naughty. We have taken Hiawatha away from some of his passions. So it turns out that once this talk is over, he gets to return to those passions, including first-person shooter games and seeing the movie Interstellar. So we'll hear about the unsolved problems of navigation. So for those of you who are feeling a little bad because you still get lost after hearing about everything else today, he will make you feel better. Our second speaker is George Hobbs, who comes to us from the Commonwealth Scientific and Industrial Research Organization in Australia, which most of us just call CSIRO, and had no idea what it meant. He's a research scientist there, and one of the really cool things he has done is put together this outstanding collection of pulsar radio data, and he actually won an award for this breakthrough archive of data. And what's really cool is that he makes, I think it's this data that he makes accessible to high school students at the click of a finger from all over the world, so they can run like real live scientific experiments that real live scientists run. And I think that's pretty cool. So he has won a bunch of awards as well, including the New South Wales Scientist of the Year, but my all-time favorite award I have ever heard of, and I kid you not, it is called the Young Tall Poppy Award. Now, what, you might ask, is the Young Tall Poppy Award? And it turns out that in Australia, a tall poppy is somebody who, sticks their head up periodically and actually says things and draws attention to oneself. And that's not always considered a good thing. But when people draw attention to themselves for really positive, constructive, good things, they actually see fit to award them. And so George is the recipient of the Young Tall Poppy Award. And on that note, I would like to invite Hiawatha to tell us about what haven't we solved.
What haven't we solved? Okay, thank you. One thing most of us haven't solved is how to do a decent PowerPoint presentation, which is why I'm not doing one. And by the way, I want to congratulate Mr. Kester for doing one of the few PowerPoint presentations I've seen recently that was really, really good. And I'm looking forward to Mr. Hobbs's because it's going to have pulsars in it, so what more do you want? But I really didn't see the point in doing it because, well, it takes forever to do PowerPoint slides, and besides, all you would have seen are things that you've seen before, like satellites and things you may never have seen or may never see again, unfortunately, like a missing Malaysian airliner, because those are some of the things I'm going to be talking about. I just finished writing this book called You Are Here, wonderful volume, makes a great gift, buy 3, and it grew out of my fascination with the fact that in about the last 100 years or so, most of the really tough problems in terrestrial navigation seem to have been, if not completely solved, then pretty largely solved. And after millennia of trying, people have finally figured out really good, reliable ways of finding their way around the world. And it's actually an amazing story of how we did it. However, if you think of this as like some war on the ignorance and war on the problem of navigation, then we're still in the midst of what you might call a mopping up operation, because there's still a lot of stuff out there where navigation remains rather problematic. And I thought it'd be kind of cool to look at some of the things that are coming along that are promising to change that. We're going to take a look at this idea of a way of making sure that our image of the world will never go out of date. And we're right on the verge of coming up with a way of making sure that our maps for, well, not 100% perfect, up to date all the time, but will be as rapidly updatable as we could probably ever need. We're also going to look at that vexing problem that we're all thinking about. How the heck do you lose a whole airliner? In that case, it's not a matter of lacking the technology, it's lacking the common sense and the willingness to spend the money to fix the problem. We'll look at some of the solutions that are out there. And finally, we're going to look at a problem that I didn't even know about until a while ago, and it made me feel so bad. I felt so stupid, because I just got through writing a book about all this stuff, about the importance of navigation and location, and then I come to find out that for millions of people around the world, the problem of navigation and location is as simple as this. They don't have an address. Nobody knows where to find them. And believe it or not, that problem is only just starting to be addressed. And there's some really clever ideas out there about how to address it. So anyway, let's start at the beginning here. I was going to talk first about one of my favorite stories about all this, which is the story of satellite imaging and how it has just tremendously transformed our view of the world, how it may very well have prevented us from incinerating each other during the Cold War, and how now it's getting to the point where it's going to be able to provide us with basically nonstop, accurate images of the entire planet. Now, you guys probably have all heard that earlier this year, Google dipped into its bank account. That's not really a problem for Google, of course. They came out with $500 million, and they gave it to a company in Mountain View, California called Skybox. Now, those of you who are real hardcore sports fans know that a Skybox is that wonderful, luxurious thing that you buy a seat in if you happen to have a lot of money, so that you can look down and watch the Patriots annihilate whoever, especially what they did to the Bears. Oh, gee. I'm sorry, I'm from Chicago. I haven't gotten over that yet. And then the next week it was the Packers. I can't believe this. It was horrible. But in any case, I'm glad I didn't have a Skybox for that. However, Skybox is a company that was founded by a bunch of people over at Stanford who wanted to basically put the last, I guess you might say, the last piece of the puzzle together in terms of the aerial or, I guess, satellite imagery of the planet. A process that really begins right after the end of World War II and the rise of the Cold War. The whole thing started, as I'm sure you remember, because basically we're a country that has just come through this horrible war. Our biggest ally is now our enemy. And the people who had experienced the horror of Pearl Harbor are now worried about the same thing being redone, only with nuclear weapons. Soviet bombers rolling in over the Arctic and bombing American cities with atomic bombs. How do you keep that from happening when you're dealing with a country that's the biggest landmass on Earth and is as secretive as, say, North Korea is today? There were whole cities in Russia built under Stalin. The United States didn't even know they existed. That's how secretive a country it was. We didn't know what was going on there. And the constant fear that they were building up some massive way of attacking the US forced the Truman and Eisenhower administration to all kinds of crazy expedients, sending planes in over the Soviet airspace that was totally illegal. A number of American air personnel got shot down and killed throughout the years, many of them we've never even heard of. And these air flights simply didn't collect enough information to be worth the horrible risk of war that they entailed. So almost from day one, they're saying, you know what we really need? We need to find some way to launch something into space and have it fly over and take pictures. There are all kinds of questions about how to do that, like the simple fact that we didn't know how to put anything in orbit. They were also worried about how would you get the pictures back. The original plan actually was to launch TV cameras into space. They were just going to launch TV cameras and just have them take pictures. But the TV technology of the late 40s and early 50s took horrible pictures. They would have been useless. And of course, there was also the little problem that they were so heavy that you couldn't possibly have put them on a satellite anyway. So they gave up on that idea and came up with something even crazier. There was only one way you could possibly take pictures from space, and that was to launch a satellite with film on board. You would actually have to basically shoot up a satellite, have it fly over, take pictures, have it go to the nearest Walgreens, have them develop, take them over. No, of course. But for all practical purposes, that's what it amounted to. And over a period of a decade, with amazing diligence and technical innovation, they figured out a way to do it, and it was called Corona. And it's funny, because the day the first capsule of film from Corona was dropped back from space was the day that a guy named Francis Gary Powers was sentenced to 20 years in a Soviet prison for having spied on Russia by flying a spy plane over their territory. So at the very moment we lose our ability to fly planes over Russia to take pictures, at that precise moment they had invented a technology that was infinitely superior. One flight, the very first flight they sent up, took more pictures of Russia than they'd had in all the spy flights up to that time. And it solved all kinds of amazing problems. This is when we found out that the bomber gap didn't exist. You know, all these bombers that the Russians were supposed to have, because they saw them at the May Day parade, they flew over their air bases, they weren't there. The bombers didn't exist. They found out later that the Russians had like 4 of them, and they just kept flying them over and over and over. And that's what they had been seeing all that time. Billions of dollars were saved immediately because we didn't have to defend against all kinds of stuff because we now knew what they had. So these satellites were developed. The Russians grumbled, but soon they developed their own. And suddenly we realized that having spy satellites made the world safer. Everybody knew what everybody else was doing. We knew they weren't sneaking up on us. They knew we weren't sneaking up on them. It was a great idea. By the 1970s, we're thinking about, well, gee, maybe we should commercialize some of this stuff. We start trying to sell some of the low-grade satellite imagery we get from our Landsat satellite, which was launched for environmental purposes. By the 1980s, the French are selling high-resolution satellite imaging, and the United States gets mad, we can't do anything about it, and soon we say, oh, the heck with it, let's let American companies start launching satellites, and they can sell their imaging too. And soon, it's no longer Cold War, top secret stuff, it's commercial. Oh, by the way, I skipped a step, because while all this is going on, of course, you had the invention of digital photography. The invention of the charge coupled device, which later won its inventors a Nobel Prize. It's one of those rare instances where somebody won a Nobel Prize in physics for inventing something that people actually use, you know? Have you ever noticed that? They never gave one to the guy who did the microwave oven, and I've never understood that. But this is something that people use. And also, it made real-time photo intelligence from space practical, because now you really could electronically transmit the pictures to Earth in very high quality. And as the 80s progress, this becomes a commercial technology available to everybody. And now you have corporations in the United States like Digital Globe, which have these huge, incredibly costly satellites. About 80% of the pictures that they shoot are still being bought by the intelligence community. But now, the restrictions on what they can sell to people, it used to be if you were a commercial entity or if you were a foreign government, you could only buy the relatively low-resolution pictures. Earlier this year, they changed the policy. These guys have satellites. This is a commercial American business. They have satellites that can be up there in space and take a picture of anything bigger than, say, 10 inches. So you can see anything 10 inches or larger from space. And now it's legal to sell those pictures to virtually anybody on Earth. So high-resolution space imagery is now for everybody. Anybody can buy it, anybody can use it. Skybox is taking the next big step. They've already launched 2 of their satellites. These satellites are very different from the ones we've seen up to now. The ones that they've had up to now have been like $700–800 million a piece. They're the size of a bus. They're just gigantic. Skybox satellites are about the size of a washing machine. The cameras in them are similar to the cameras you find in cell phones. They put an array of cameras in them, and they use software to enhance the pictures. And they are able to take pictures of stuff with sub-meter accuracy, as they say. And they have already launched 2 of these satellites, and their ultimate plan is to launch 24 of them in relatively low orbits. And the idea is that these things are just going to fly over the Earth, much like GPS satellites are constantly in orbit, so that like 7 or 8 GPS satellites are always over us at any given moment. Same thing with these, only when these pass over, they're taking pictures. They estimate they're going to be able to take pictures of the entire planet for at least 3 times a day, even more. So you will have our picture of the Earth constantly updated, constantly. Every time you look at Google, because Google owns them, remember. I don't know how quickly they will plan to update their images, but in theory, we could have a future world in which what you see on Google Maps, instead of being a picture of, say, Milwaukee, that's 10 years old, or 2 years old, or 1 year old, it'll be a picture they shot yesterday. That's the world we're entering, a world in which we will have near real-time pictures of the planet. And I think it's going to be absolutely fascinating. They're already figuring out things you can do with it. What's going to happen in an earthquake zone? It's going to just transform disaster relief when you will be able to fly over an earthquake zone within hours, sometimes within minutes of a disaster, and see exactly what's going on. If you want to know what crop yields are going to be anywhere in the world, that's okay. Just go over every day and take a picture. You'll be able to figure out how many bushels per acre you're going to get. You want to know what Christmas sales are going to be like? Fly over the parking lots. No, this is true. They've done the work. If you count the cars in a shopping mall parking lot, they have found that you can come up with a very accurate estimate of what sales at that mall are going to be. So they're going to be able to fly over and count the cars in every mall's parking lot. Every mall here, every mall in Europe, every mall in Asia, and they're going to be able to come up with remarkably accurate economic estimations just off that. And the people who run Skybox are telling us, we still don't know all the stuff you'll be able to do with this. We're waiting for people to come to us and tell us what you can do with this technology. It's going to be amazing to live in a world when you can actually have accurate pictures of the entire world all the time. So that's one example of something that I find fascinating. The other examples, Well, one of them is particularly grim and grisly, and of course I refer to the real nightmare of losing a whole great big commercial airliner. It's kind of spooky. As everybody knows, on March 8th, Boeing 777 just disappeared. I mean, man, can you imagine, by the way, Boeing having a rotten year with the 777? Up until this happened, it had probably the best safety record of any airline in the world. They hadn't had a fatal accident at all. Then in 2013, you have that crash in San Francisco where the pilot screwed up. Then you have this plane disappearing. Then you have one getting shot down. Boy, I mean, they just had a really bad run with that airplane, but that's not their fault. The thing about the 777 is we don't know why it went down. Was it some flaw in the plane that nobody previously guessed? We can't tell because we can't find it. And we can't find it because they weren't telling anybody where they were. Why is it that a plane can fly over the oceans of this world and we don't know where it is? Everybody assumes it's on radar. You get a couple hundred miles out to sea, you're no longer on radar. Now, you can send information electronically using a variety of systems built onto the plane. This plane particularly had a system called the Aircraft Communications Addressing and Reporting System. We don't know why, but it apparently was turned off. There's a secondary system, though, based on the same technology that kept working. That's why they think they have a rough idea of where the plane crashed. That secondary system simply sends a ping to a satellite network. But that ping doesn't really contain any information. It just says, I'm here. But it doesn't say where here is. It says, this plane's satellite radio is turned on. But it doesn't say where the plane is. And because of the lack of that technology, we don't know where that plane went down. Well, that is going to have to change. And in this case, it's a matter of a whole bunch of technologies that are known, but it's basically stuff we know how to do, but we just haven't implemented it yet. And now, thanks to this horrible disaster, we're on the verge of doing so. Consider, for example, Inmarsat, which is the satellite company that runs this system that was used to at least identify the fact that the plane was still pinging. In May, they announced that they are now going to change the way their system works. The system that automatically pings airplanes, which, by the way, is built onto 80% of the world's long-haul aircraft already, so it's already on the plane. All they have to do is turn up this new feature. When it pings, it will simply include the plane's location and heading and speed. It will automatically say, and this will happen every 15 minutes. The current ping happens once an hour. From now on, a plane equipped with this technology, every 15 minutes it's going to say, I'm here, I'm at this altitude, I'm going this fast, and so on. So if anything happens to it, they'll have a fair idea of where to search. But that's just the beginning. If you're flying inside the United States domestically, we have a system called I hope I'm pronouncing this for ASDB. Oh boy, it's got an acronym that I should look up and make sure. ADSB. Thank you. ADSB, which is a system that automatically relays that kind of information to ground stations all the time. It's constantly pinging the ground stations to say, I'm this plane, I'm at this altitude, I'm at this speed. But it's not designed to work over oceans because it relies on ground stations. And when you're out of range of the ground station, you can't get it. So a company that is working on this problem is called Arion, and they are going to be building a solution to it. You all know about the Iridium satellite radio system. They're getting ready to launch a whole new generation of Iridium satellites, and this set of Iridium satellites is going to have it's going to have antennas for picking up ADSB signals, so that wherever you are in the world, the ADSB signal will not just go to a ground station, it'll go to a satellite station. If this had been on any plane, actually, out over the deepest part of the ocean, then it would have automatically sent out its location information constantly all the time. This is supposed to be available by around the year 2017. The other final thing that people are finally starting to take seriously is something that was first brought up, well, not first, but it really was a big hot button issue in the aviation community back in 2009, which is the last time a plane disappeared like this. Fortunately, in that case, for a very short period of time. I refer, of course, to Air France 447, which just dropped out of the sky. It took them a day or two to figure out where that one had gone, although it took 2 whole years to actually find the wreckage. And by the way, I got to have dinner in the company of one of the ladies who worked at the Woods Hole Oceanographic Institute. She was at the dinner last night, and they were the people who finally figured out where the wreckage of that plane had ended up. Anyway, that particular airplane got people thinking that it took them 2 years to find the black box under 13,000 feet of water, and what if they had never found it? They'd have never known what caused that plane to crash. Why don't we solve that problem by taking black box data and transmitting it by radio? Why do you have to have it so that you can only hear what was on the black box if you can find the wreckage of the plane? Now, a radio version of the black box wouldn't be as comprehensive as the one that you have where it has a complete recording of everything that everybody was saying on the flight. It would be designed so that if the engines cut out, for example, or if there was explosive decompression, the plane would immediately start transmitting all kinds of technical data about the status of the plane. It would transmit it to a satellite, which would be transmitted to a ground station. And so you know what had basically happened. This could have been done years ago. There's a company in Canada that makes a system like this. Nobody's using it. It would cost something like, I think they said something like $100,000 per plane to add it on. Well, it looks like they're going to start adding it on. And in fact, Inmarsat is also going to add that capability to its satellite networks on planes. So you can see that in the case of Malaysia 370, the problem was not a matter of having to invent new technology. The basic know-how of how to solve this problem is with us, but because of economics, it was decided that it just wasn't necessary. That, plus we were lulled into a false sense of security by the wonderful reliability of modern jets. I mean, it's amazing how reliable these things are. It seems almost unimaginable that one could fall out of the sky. But we've learned the hard way that they can. And so now at least we're taking this seriously and we're going to apply modern navigational techniques to finally get this problem under control. Okay. Last but not least, the one that really shocked and appalled me, not having an address. I mean, I don't know about you guys, but I live someplace. And so do you. And it's easy to find you. You know, 123 Elm Street, whatever. That whole approach to numbering buildings and giving a sort of a neat, reliable, accurate way of figuring out where people are really was born in 18th century Europe. It really is relatively new. I mean, if you'd shown up in a city 500 years ago, you'd have just said, okay, he lives 3 doors down from the cathedral over in the market district. That's how you found people. And it was very difficult to have an objective, reliable way of tracking people down. Then this whole numbered idea comes along in the 18th century. Everybody adopts it, and now all of us have addresses and we're easy to find. Not true. It's true in much of the industrialized world, but there are huge swaths of this planet. For example, we're now in a world where, as of 2008, most of us live in cities. There's been this massive urbanization where people move from the countryside in places like China and India and rush into cities. And often they're moving into these cheaply made hovels, these shanty towns that were just thrown up as places for them to live, and where there has never been any official mapping of street addresses for all of the homes and businesses involved. And so people don't have addresses. And that might sound like a trivial question until you stop and ask yourself about your own life. If you don't have an address, how do you register to vote? How do you get mail delivered? How do you call the police or get an ambulance when you're sick? That's a particularly vexing question if you live in Liberia, because in Liberia, they never had a system of street addresses. If you live in Monrovia, Liberia, you can't say, I live at such and such a street, because they never assign an address to you. And if you happen to live in a city where a deadly disease is slowly but steadily killing thousands of people, one of the things you'd like to be able to do is know where the people affected by the disease live. You want to be able to do contact tracing, and it's hard to do contact tracing if you don't know somebody's address. So that's one of the reasons why the government of Liberia started talking to a guy in Utah who invented a solution to the problem. This guy started a foundation called Addressing Homes. He invented software that allows you to look at a Google map at houses depicted in the photo and calculate the exact latitude and longitude of every address. Then he came up with an algorithm where you feed that latitude and longitude in, and it assigns a numerical street address. It's an objective address based on latitude and longitude. You could use this method to address every part of the planet, but he particularly wants to use it in areas that currently do not have addresses. And they're working with the people in Liberia to start deploying this technology. In some cases where you can't see a house using a satellite map, they're going to take this $8,000 device, which has a GPS receiver in it, a satellite radio, and a camera. People who work for the government will walk up to the house, read the latitude and longitude, take a picture, push a button, transmit the data via satellite to the government offices. And each of these places will now be assigned an address. Then somebody comes back later with a piece of plastic with their new address written on it. It says, stick this next to your door. You now have an address. You can now be found. Disease tracking can go on. Mail delivery can go on. You can register to vote. You can open a bank account. You can take part in the modern world, maybe for the first time in your entire life. An organization in Ireland run by a direct mail business expert named Alex Pigot, called GoCode, is doing the same thing in India. He's been working with people in the slums of Calcutta. And basically, they have taken this area of about 250,000 people. It's basically a squatter's camp, and nobody has an address. And they are going through and using a similar technique to assign geographically based addresses to every house and business there. And already, hundreds of people in these neighborhoods have seen their lives change, because now people can find them. And they're no longer a mystery to the government. They're no longer a mystery to the businesses in the area. And they now have real existence in the modern economy and modern society. We take so much for granted in our own society, and that's why we get wowed by the GPS and the satellites and the imagery and all that. But something as basic as simply having a specific place where you can say, this is me, this is where I am, here is where to find me, can change somebody's life tremendously. Little by little, we're going to solve this problem and all the others. And it's going to take a combination of hard work, of course, and brilliant technical innovation, but also a willingness to really stop and think and understand from the point of view of other people the importance of having a place on the earth, a specific defined place of one's own. And that covers what I have to say. Thank you very much.
Okay, well, thank you very much, and thanks particularly to the organisers for inviting me across here to this excellent symposium, and also to this very cool city. This is the first time I've been here, and in all senses of the word, this is a cool city. And also, it's a very confusing city. I arrived a day and a bit ago and got totally lost last night. I couldn't find this place, I couldn't find anywhere. And that started making me thinking a little bit about, if I can't find my way around Cambridge and Boston, how would I find my way around the galaxy? And that's the whole purpose of my talk, because we're now going to go out much, much further and talk about navigation on a much, much larger scale. So I want to start with this plaque. This plaque was a message put on the Pioneer 10 and 11 and some of the Voyager space probes. So this is a picture of the Pioneer 10 space probe that was launched in the 1970s. These space probes were meant to travel through our solar system, studying the planets, studying objects in our solar system, and then just to keep going. And what they thought, the NASA engineers, was that one day, maybe in hundreds of years, maybe in thousands of years, maybe in millions of years, some alien might suddenly say, oh, what's this thing going past? Pick it up, have a look at this thing, and be able to work out where it came from. And so they made this plaque. Now, it's a long way from Australia to Boston, and so I spent the time pretending I was an alien trying to decipher this plaque. And I think you're going to have to be a very intelligent alien to be able to do this, and I'll certainly challenge anybody in this room to just look at this plaque and work out where we are with respect to any alien in our galaxy. But I'm going to come back to this slide later in my talk to actually explain what all these lines are. But let's first just take a step to the side. What I'm going to do now is I'm not going to pretend, I have a big radio telescope. We're going to point that telescope at a particular patch of the sky, and instead of doing really complicated things with supercomputers and so on, we're just going to plug it into some headphones. And so this is actually a real recording from a telescope, and it's what happens, you take the signal, you just plug it in, and you listen to the sound. Normally when you do that, it's just like tuning your radio between stations. You get some static, you get some hiss, and a lot of astronomers spend their whole life getting excited about this noise. And sometimes it gets a bit louder, and sometimes it gets a bit softer, and these astronomers get very excited about this. But there's some very, very special parts of the sky. And so this is the sound from one particular part. So can you hear that click? I say again, this is the real signal. This one I think was from the Jodrell Bank telescope. When this was first discovered, not this particular one, but one that sounds very like it, was discovered in 1967 in Cambridge in the UK by Jocelyn Bell. She and her supervisor recorded this as LGM1, standing for Little Green Man 1. Whether this was very serious or not is still not clear, but it was certainly recorded as a potential signal from an alien civilization. However, we now know of quite a few more of these. So here's another signal coming from space. This is in a different direction in the sky. here's another one. If you listen carefully, some of the pulses are missing. We have no idea why. So if anyone can come up with an explanation for why suddenly a pulse will be missing, the one you just heard, I'd love to know. We do not know why these pulses disappear. I don't know how to stop it. Hang on. So what is this thing in space that's making this? It sounds like a heartbeat. Some are very fast, some are quite slow. What's making that signal? Well, to find that out, you can go and take one of these examples. This is the sound with a radio telescope. But if you use an optical telescope and point at this direction of the sky, you'll see an object that looks like this. This is what we now call the Crab supernova remnant. And you say, well, that looks very pretty, and there's lots of colors, and clearly something's happened in this position in the sky. So if you want to know what happened, and I think this is amazing, you go and find an ancient Chinese astronomer from 1054. This is some text that was actually written in 1054. This is the closest I've got to an ancient Chinese astronomer. He's my student, or was my student. And so I asked him to read this text. And what it is, in case you speak Chinese.
宋祖和元年5月己丑，克星出天关，东南可数寸，岁余烧没。
So we hope that's clear to everybody. If you want a translation, what it says is this.
July 4th of 1054, and there is a guest star from the southwest of the sky, and more than 1 year later it has disappeared.
So what happened is the Chinese astronomers saw that suddenly in a patch of sky there was a big bright light. And it lasted for a very long time, and then over time it slowly died away. And one thing that's always interesting to me is it seems that people in North America at the time actually also saw this event, and possibly people in Mexico. People in Europe didn't see this at all. Maybe it was cloudy for the whole time. I have no idea why the Chinese saw this, but the Europeans did not see this event. We now think we know what happened, and here's a little cartoon of that. The star came to the end of its life. It ran out of fuel. As it ran out of fuel, the whole star will collapse in on itself. It will bounce off the central core of this object. That bounce will cause a big shock wave or a massive explosion, which we term as a supernova explosion. A lot of the star gets just thrown out into space, so all the guts of the star just gets thrown out, and that's the sort of pretty picture that we saw from this position in the sky. But the question is, what's left over right in the center? And if you do the modeling of what happens when a massive star explodes, the central region doesn't just disappear. The central region collapses in on itself until it forms an object that's only about 20 kilometers across, extremely dense, and can be spinning very fast. And what we believe we're seeing when I play these sounds is exactly that. It's the remnant core of a star that's exploded. This is just a little cartoon. The star's about 20 kilometers across. It has a massive magnetic field. At the north and south poles of the magnet, you get these beams of emission. And it's just like a lighthouse rotating. If the beams are pointing in your direction, your telescope's in the right place, you'll get a flash of light as that pulsar rotates. And it's those flashes of light that you can detect with a radio telescope, and those are the sounds that I'm playing to you. The slowest one we know rotates about once every 10 seconds. The fastest one we know goes 720 times a second. And if you play the sound of that, it's pretty incredible. So what you're hearing here, every pulse, and you can't even make out the pulses, is a rotation of a star in space, more massive than our sun, only 20 kilometers across. The surface is moving almost the speed of light. These are extremely incredible objects. And 720 times a second is quite hard to imagine. So it's actually faster than a kitchen mixer. So if you have a mixer and you're making your cake, that's going slower than these pulsars. And I know that because I looked up the speed of kitchen mixers, and they are not as fast as these amazing stars. So this is what we think we know about pulsars. They're very, very small objects. They're only 10 to 20 kilometers across. They have more than the mass of our sun pushed into this tiny region. They're not made of normal matter. They're made from neutron degeneracy, the pressure. It's a very strange quantum mechanical effect. They've got this huge density. If you just have a thimbleful of this, it will be 10 to the 9 tons. These are extreme objects we're talking about. They can rotate once to several hundred times a second. The acceleration due to the gravity, because it's incredible mass and small size, is absolutely huge. They have enormous magnetic fields, and currently we know of about 2,000 of these objects. So why do we care? And I want to just give a little cartoon of my main research topic, and you'll find it's got nothing to do with navigation at all, but I think it's very cool, so I did want to show you this. But there is a link, and my research into navigation came from exactly this project. So in the distant universe, we assume we have massive galaxies. Those galaxies, we think, have supermassive black holes in their center. We know that galaxies crash into each other, merge, and the black holes get closer and closer to each other. These things are representing the black holes, and these are billions of times more massive than our sun. This green mesh is the warping of space and time that Einstein predicts will happen if you have two masses moving around each other. This warping is known as a gravitational wave, and this can propagate out through the universe. This is a representation of everything important in our galaxy. There's the Earth with our telescope. This is not to scale, I hasten to add. And you have a pulsar. That pulsar is emitting these pulses, which we heard. But as the gravitational wave passes, it wobbles the position of the pulsar a little bit, and it wobbles the position of the Earth a little bit. And so those pulses will seem to arrive a little bit earlier or a little bit later than they would if these gravitational waves weren't there. And so we're studying a large number of these pulsars, and we're saying the pulses are arriving a little bit earlier or a little bit later, and we're trying to prove that that must be due to these gravitational waves passing our Earth. Nobody to date has ever been able to detect these waves. But we have a problem. And the problem is, to know if the pulse is arriving a little bit early or a little bit late, we need to know when it should be arriving. And unfortunately, the predictions from general relativity says if you observe this pulsar for maybe 5 or 10 years, you might see fluctuations in these arrival times of about 10 to 100 nanoseconds. So this is a tiny effect. And in fact, atomic clocks aren't good enough at 10 nanoseconds over this sort of time scale. So you have a big problem of how to measure these arrival times. Another problem is we need to know where we are. Of course, if the Earth was a little bit in this direction, the pulses will be arriving a bit earlier than if we were in this direction. And measuring pulses at a telescope is a very silly thing to do, because the telescope is on a rotating Earth, and so it depends on exactly when you make the measurement. But that's okay, you can correct to the center of the Earth. But the center of the Earth is moving around the sun, or the center of mass of our solar system. And that's a big effect when you're talking about 10 nanosecond timing precision. And to make it even worse, the sun in our solar system is moving around the center of the galaxy. And so to know when a pulse should be arriving, you have to try and account for all these effects. And so hopefully you can see here that there is a link to navigation. To be able to do this work properly, you need to know where you are. But you can reverse the process and say, I think I know everything about the pulsars, but I don't know where I am, and I will use the pulsars as basically a galactic scale GPS system to actually pinpoint my position in space. And that's not pinpointing my position on the Earth's surface, it's pinpointing your location with respect to the center of our solar system. So we can now talk about navigation across our solar system, or perhaps even beyond. So let's just change the topic a bit and talk about the GPS system. Now, I'm sure there's a large number of people here in the audience that use the GPS to get here. Everybody uses GPS. I'm sure if you haven't used it today, you've used it last week or sometime. Everybody is using GPS. And so we use it, aircraft uses it, the military people use it for mapping. There's lots of people that use GPS. But there's problems. One, GPS can be jammed. A second problem is somebody could decide to switch it off. A third problem is a big solar storm could just knock out all the satellites. There's a lot of things that could happen, and yet we're so reliant on the GPS system. And so just in a wonderful book I was reading recently, this author was discussing what would happen if the GPS failed. And he ended up describing it as it would be catastrophic. If GPS disappeared today, it would be a massive problem. Another issue with GPS is that these satellites are in low or mid-Earth orbit. If you want to travel to Mars or a distant star or somewhere else, of course, you can't use satellites that are only around our Earth. So let me just go back now to this plaque that's on the Pioneer spacecraft. This is representing where we are, and these lines represent distances and positions of 14 pulsars. Unfortunately, at the time they did this, one of the pulsars, which is this one, is in the wrong place. And so I hope if an alien discovers this, they will just ignore this one, which is a bit of a problem. And of course, how do you know what the pulsars are? Well, if you could zoom in on these lines, these are actually binary codes telling the period of the pulsar. Now, how a random alien would know this, I have no idea. But these will uniquely identify different pulsars, just like we can uniquely identify different lighthouses for navigation on Earth. And so hopefully, if they can see enough of these pulsars, and remember that to see a pulsar, the beam has to be pointing at you. So if you go somewhere else in the galaxy, you might not be able to see the same pulsars that we can see at the moment from Earth. And it would be a very good puzzle for some students to work out if you go anywhere in the galaxy, which pulsars would you be able to see compared to the ones we already know about on Earth. So the basic idea to use pulsars as a galactic scale GPS has actually been known about almost since the discovery of pulsars. It's certainly been talked about since the 1970s. This map was, I think, the first actual use of using pulsars as a galactic scale GPS. But I'm sure everybody knows the system that you use to navigate here today didn't have anything to do with pulsars. And so now the question is, can we move away from GPS and actually use pulsars as the GPS satellites instead of the actual satellites? And so this is great because you can make really cool looking pictures. This is a picture from some Europeans working on this project. And the idea is very straightforward. You've got, of course, your spacecraft that's just heading out through the galaxy somewhere. You've got a pulsar that you can detect coming from this direction. You've got another pulsar from this direction. If you have 3 pulsars, you can work out exactly, in quotes, exactly where you are in space. If you have 4 or more pulsars, you can even work out what the time is. So with this technique, in theory, you can measure both time and position. So that's all fun, and you can enjoy making little pretty pictures of spacecraft moving, but does it actually work? So we decided to use some of the data that we collected for this gravitational wave project and just see if it works or not. So the advantage of this project is that we used a particular telescope and we know where that telescope is. So we can try and work out using the pulsars where it is, and we can compare with our actual knowledge of where the telescope is. So first, you know it's in Australia because of all these kangaroos that are standing around. And if you take the telescope and you just observe one pulsar for a very short amount of time, you've only got one direction. It's like seeing one GPS satellite. And if you know you're on the Earth's surface, you then get a sort of grid, and you could say, I don't know where I am, but I'm somewhere in this grid. And the width of this represents your uncertainty in measuring when the pulse arrived at your telescope. So that's fine, but I don't think anyone would be very impressed to know that we're somewhere in this region. The position we actually are is this blue dot here. But if you then don't move, which you can't if you're a big radio telescope, and you point at another pulsar in the sky, which is in a different direction, then you can say from your original observation that I'm anywhere in this direction, and you can say with your next pulsar, I must be anywhere in this region. And so you can see that as you observe more and more pulsars, your positional estimate gets better and better. And if you observe one of our brightest, most stable pulsars as a third pulsar, you get down to this. And if you actually go to Google Maps and work out where we predict the telescope is compared to where we know it is, in this particular case, we were correct to about 1 kilometre or so. And so that's not very good compared to GPS, but this is completely independent and has no knowledge of any GPS system. The problem is it's a bit hard to put something like this on the top of your car or on your watch or whatever you want to be using. So the question is, can you make it smaller? And also, can you do it for something that's actually traveling through space? So my student and I had a go at this, and so we simulated observations of a few pulsars on a trajectory going from the Earth to Mars. And we used the most realistic simulations we could. We took gravitational field effects into account and solar pressure and everything else we could think of all went into the modeling. And then we assumed that the telescope on board the spacecraft was quite a small X-ray telescope. And for any astronomers in the room, this was just like the XTE satellite that already exists. People know its properties. So we assumed that there was this spacecraft going from Earth to Mars, and on board was this X-ray style telescope. And there's so many different possibilities. That telescope could be talking to a ground station, or it could be fully autonomous. You might know something about where it was in the past and which directions it's moving. Or you might just say, I know nothing about, I'm somewhere in space, I've just turned on my detector. So we trialed 2 algorithms, one which is, I just switch everything on, I want to know where I am. And the other is, I know where I was maybe a week ago, and I know I was in an orbit moving in this direction. We found it didn't really matter which algorithm you used. In both cases, you could get your position to about 10 kilometers. And again, for GPS, that's not very impressive, but this would work anywhere in the galaxy. So in theory, you could work out where you are to about 10 kilometers as you go traveling off to a nearby star. And you can actually measure your velocity as well with the same method. So the question is, will this actually work? And I think a few people around the world are working on this, and I think I can truly say that the technique, there's no obvious mistakes in it. If you want to travel for deep space navigation, this technique will work. But you do need something like an X-ray telescope or something on board to be able to do this. And people in the US, people in China, people in Europe, people in Australia are working on various techniques and implementations. The US have a very interesting idea of actually putting one of these X-ray detectors on the International Space Station to prove that it actually works in the next few years. The China also are planning to launch spacecraft with pulsar-based detectors on board. This is just a personal comment because we haven't done enough work. I think for deep space navigation, where everything changes quite slowly, I think this will work. If you want to know where you are on Earth, and the Earth's spinning very fast and moving around the sun, I think we need much more sensitive detectors than we currently have. But we're still working on this, but I basically think unless you have a big telescope, you're not going to be able to find your way on Earth using this sort of method in the near future. But one day, I think we may be able to leave our solar system and navigate to other stars using the pulsars. And just to finish, but I do hope on my flight back to Australia, the GPS is still working. So thank you very much.
So I think we'll open the discussion by seeing if either of our speakers want to ask anything of the other. In the meantime, you should be thinking about the questions you want to ask. So would either of you like to ask anything?
I just thoroughly enjoyed that, but I guess I was curious as to how people were planning all along to navigate. I mean, if this doesn't work, is there any alternative way of figuring out how to navigate beyond the solar system? Because I guess it's something I didn't realize people hadn't thought about before.
It's a very hard problem. So, of course, at the moment, if you want to navigate the NASA or European or Chinese spacecraft just to Mars or to even the distant objects in our own solar system, they don't use these methods. They use knowledge of the positions of stars from optical imaging, and they use radio telemetry back and forth to the spacecraft and so on. All of these effects get sort of worse the further out you go. And I think people have assumed that stellar travel is so far away, we're not going to worry about it. But for solar system travel, you can use existing techniques.
Do you need to use it for solar system travel? I mean, won't existing can't. Oh, go ahead.
So for obviously, like NASA can easily get a spacecraft to the right sort of point on Mars. Biggest problems are if they're trying to work with a spacecraft that goes behind an object, because all of these techniques basically involve some telemetry back to Earth. The other thing is if for some unknown reason you wish to have a fully autonomous system that has no connection with Earth, then currently there are no real techniques for doing this. But in terms of just a general, I want to send my spacecraft to Mars and land it, and I've got a direct line of sight, that does work fine at the moment.
Okay, while you guys are working up your nerve, I actually have a question. So this placard, this is real. Like, they actually sent this placard thinking that it would transmit real information to somebody who found it.
Yep. One of the big, I was reading about this on Wikipedia, which I get all my knowledge from, and it told me two things. One is that there was a lot of complaints about the use of an arrow. So there was an arrow, I don't know if you remember, going out from the Earth, and the arrow is so specific to our culture, or at least that's what a lot of people say, is it would have been meaningless to everybody else, or to any alien. The other thing people have complained about is that people are naked. Apparently this is a terrible thing.
Yeah, but I'm sure you've heard the people talking about the whole question of whether we should even have done it, the ongoing controversy as to whether or not we want intelligent civilizations. I mean, you know, H.G. Wells' War of the Worlds was partly inspired by the European experience of colonizing less advanced civilizations. And he basically said, if a more advanced civilization runs across us, won't they act the same way that the British did when they encountered India or something like that? Do we want them to find us? I guess you have
Was that a question?
Yes. Yes, it was. Do you want them to find us? Are you one of them?
I think we are sending out so many signals with our radio, TV, radar, so on, that I think it's more likely any extraterrestrial signal will be, a civilization will be picking up those signals.
Well, they have to be within, like, what, 60 or 70? We've only been sending them out for...
that's true.
Right, they have to have been within, like, 60 or 70 light years of us.
Right, but
Right.
That's going faster than the spacecraft. And that's only a few of them. So I think it's more likely they'll find that signal.
Okay, so as we ask questions, please introduce yourself and then ask away.
Kevin Healy. Regarding the placard on the Voyager, it looked to me like those pulsars were represented in a plane. Wouldn't you need to have them depicted in 3D to actually tell you where the Earth is?
So that's actually a very good question. It shows the direction. I think one of the numbers that is encoded is a distance, and then there's definitely the period of the periodicity encoded. And I think with that information, you can find the actual position of the Earth. So I think it's fine. As I said, I tried to solve it on the flight out here and totally failed. So I challenge somebody else to actually try and do it, but I do believe it is possible with the information given.
Maybe if you flew business class.
Yes, that's right.
Hi, my name's Caleb Berry. I wanted to first thank you both. I thought those were both excellent talks. I had a question for you, the first speaker. I was wondering, I know this is a sort of complicated and hot topic, and so I'm assuming that you won't be able to answer it entirely now, but I was wondering if you could talk a little bit about the relationship between the technologies you've discussed and privacy.
Well, yeah, it's a very complicated topic, and there aren't any easy answers, because so much of this stuff, certainly in the case of a lot of our cellular communications, is inherently revealing. The minute you turn on a cell phone, you're telling people where you are. The minute you use a lot of these features in Apple or Google, you are telling Apple and Google where you are. Now, they are insisting that they don't really track you, they track the device, and I believe them. They have no particular reason to want to do it. But there is this growing list of stakeholders who know where you are. We haven't even counted the fact, increasingly people are giving their attention to this. If you have a cell phone, the company is using your location for marketing data. For example, they track whether you go to bars or museums or churches or whatever, and then they use that to decide what kind of ads that you're going to see when you use your telephone. But they insist they don't know who you are, and again, I tend to believe them. That said, though, there's the increasing problem of how governments are using this data. They are basically using these corporations as proxies, and they basically say, well, you guys are collecting it anyway, here's a warrant, give us what you've got. In addition, wasn't it just yesterday or today, I think it was it the Washington Post or the Wall Street Journal just had this story about how they're using aircraft-mounted phony cell towers to intercept our cell traffic. Well, they do pass it on to the real cell network, so the calls seem to be going through, but along the way, they listen in. And this kind of thing is becoming more and more pervasive. And the only way to really deal with it in the long run, I think, is through legal and, I guess, governmental means where you set legal restrictions on what can and cannot be done. Because like I think most people, I love having the technology and I don't want to have to give it up. So what I would like to see instead are very strict limits on its use. I mean, for example, the US versus Jones case, where the Supreme Court ruled you can't put a GPS navigator on a person's car without a warrant. But some of the justices right across the spectrum, conservative and liberal, wanted to go further, and I agree with them. They were saying, look, your phone is already a GPS device, and you should have to get a warrant just to get the back tracing of all the places where you've been with your phone. And I agree. I don't want to lose that locational ability. I just want to stop the government from doing whatever they feel like with it. And it is a real issue.
Hi, my name is Peter. I'm actually in the physics department. I work with NASA, and I actually got rid of my phone a year ago, so I actually do not get tracked all the time. I had a question actually about the future of the technology for terrestrial detection of the pulsars. And I guess there's always this trade-off, right, in terms of you're detecting something between how long it takes, right? I mean, ostensibly, if you had a weak signal, you could collect for long enough to get a precise signal. So is it possible, for instance, going back to the search and rescue ideas, that maybe you're in a place where you can't see a GPS satellite, could you see some pulsars, you leave it out there for an hour, and would it be able to, for instance, refine your location? I mean, I don't know enough about the physical detection of the radio waves. Like, is it going to be possible to have a personal-sized device, or is that impossible?
Yeah, so this is exactly what I'm trying to work on, and I'd like to answer this question. All the literature, or almost all the literature on this topic, is for deep space navigation, and they've gone to X-ray telescopes because they're quite small. The problem with X-ray telescopes is they won't work in our atmosphere. So if you want to do this on ground, you have to go back to the radio telescopes. And as you say, you can't have a huge telescope. You have to have something that you could carry around or put on your car or something reasonable.
Well, dumb question. I assume you're saying then that a radio telescope must be larger in order to pick up the waves as opposed to an X-ray telescope.
Yes, so radio telescopes are much larger. So at the back of the envelope calculation that we did just a week or so ago, and may be wrong, is that to observe the brightest pulsars in any reasonable time, like just in a few minutes or so, you need 10 square meters of collecting area. And that's
You mean on Earth?
On Earth.
Right.
But that doesn't necessarily have to be a huge metal thing. It could be just some mat you put on the ground or something. And maybe with new technology that could get smaller. Who knows? I don't know. But yes, the other thing you can do is just integrate longer. So if you don't actually move and you want to sit there for 6 hours or something, you can just keep adding the signal on top of each other. The problem with that is we're referring everything to the center of mass of our solar system. And in a few hours, the Earth has rotated and the Earth has moved. And so you have to be able to model that effect. And if you can model that effect, then I think, yes, you can just sit on the Earth and keep integrating. But actually how to do it is not a solved problem at the moment.
Thank you.
Great talks, both of you. It's a shame that Joyce Owen Bell didn't get the recognition that she should have at the time and died before, much too soon.
Could you introduce yourself, please?
I'm Eric Rattan. Carl Sagan and the others that were involved in this, sending the Pioneer out with that information, I think they assumed, and probably, possibly correctly, that any alien intelligent life out there that would find this would presumably be more peaceful and much better down the road as far as not inflicting violence on others, and who knows if that's true or not. But my other question is, I think back in 1960 there was a model for using 7 steps on estimating the probability of intelligent life on other possible planets. And has that gone by the wayside? Are there any new models that might predict the probability of intelligent life surviving long enough on a planet in a sweet spot around a good sun?
Okay, so great question. Just a quick comment on your first point in case anybody didn't know. This is an issue that rankles in the pulsar world. So the discovery of pulsars was made by Jocelyn Bell, who was a student at Cambridge at the time, and a Nobel Prize was awarded to her supervisor. And this didn't go down too well and is still a bit of an issue. But anyway, that's in history, I guess, and hopefully that sort of thing doesn't repeat too much. In terms of the question, I think you were referring to the Drake equation. That's a prediction that was made on what's the probability of extraterrestrial intelligent life existing, depending on a whole range of factors. My understanding is that actual equation has not significantly changed since it was first described and discussed. The big change that's happened in the last few years is the huge number of extrasolar planets that have been discovered around a large number of stars, and there's a lot of talk about habitable zones, and that's knowing a particular star, where would an intelligent life actually be able to survive? How far out would that planet have to be? And those numbers, where now people are actually detecting these things and saying if you look at so many stars, you have so many planets, so many of them are in these habitable zones, that's actually improving the estimates for the Drake equation, and I don't off the top of my head know any updates, but I don't think anyone's particularly changing the equation in any way, so I don't think there's any new research in that area that I know of.
Well, personally, and this is not, obviously I have no expertise in this, I've been reading about this for years, and I'm a Fermi paradox man. What can I tell you? I always respond, where the heck are they? If there's all this intelligent life, we should have heard by now. I can't help thinking. No, I'm perfectly serious. That was, Enrico Fermi's famous answer. If life has been swarming around the universe for billions of years and intelligent life is commonplace, where is it? We, just by sheer accident, have been broadcasting our existence out into the universe for, 60, 70 years now. And so anybody within that range of light years knows we're here. So if somebody 1 million years ago had an intelligent civilization, if they were 1 million light years away, we'd know by now. Where are they? I'm just not convinced. I should say in my own personal opinion, I think there is intelligent life out there. I'm just saying I just don't see how you can mathematically assume that it's common. Because if it were common, I think we'd have heard.
Can I just comment on
Absolutely.
that? The biggest question I have is, we know that there's an awful lot of life on Earth.
Yeah.
And there's not much of that life we can communicate with, even though a lot of it is quite intelligent. Mm-hmm. And so why would expect, if we can't communicate particularly well with a giraffe or something, how would we expect to be able to communicate with some completely different extraterrestrial civilization? Yes, we are sending out signals, but so are giraffes, and so are lots of other things, and yet we can't really communicate with them. I'm not sure if I really just said that.
Let's go to the next question.
Joseph Coors from Pennsylvania. I have 4, I think, simple questions. One is, you mentioned the Crab Nebula. Is that part of the Milky Way?
Yes.
Okay, I think you also mentioned there were 200 known pulsars. Are they all within the Milky Way?
So there's 2,000 known pulsars. In fact, it's about 2,500 now. Almost all of them are in the Milky Way, and that's because pulsars are quite weak objects. So we believe that there's pulsars all over the universe, but we can only detect at the moment with our current telescopes the close ones. So almost all of them are in the Milky Way. There's a few now known in the Magellanic Clouds, which are companion galaxies to our galaxy. Okay. But we don't know any further out. The new generation of telescopes will, we hope, be able to see pulsars in nearby galaxies.
Okay, you answered the third question. The fourth question is, you mentioned navigating the solar system. Wouldn't they also be useful for navigating the Milky Way?
Absolutely. So okay. I think on the longer term, that's probably what its main use will be. in the end. Because as I said, you can already navigate the solar system with existing techniques. But if you want to go out further, you have these issues, and pulsars are at least one way to deal with that.
Actually, I'm going to ask one last question before I turn it back over to John, and this is back to Hiawatha. So I want to get back to this question about the intersection of privacy and technology, right? So Skybox, you might say is no worse than the fact that your cell phone can track you, but my intuition says there's something different about pictures.
Well, yeah, but I mean, we're talking pictures here of, like, I think it's objects like 10 inches or larger is what they can
I'm
resolve.
bigger than 10 inches. I don't know about the rest of you, but I'm definitely bigger than 10 inches.
Well, no, I mean, it wouldn't be too hard to think of ways you could use something like that to do some measure of tracking. But I'm not sure that's the primary problem, because there are other terrestrial methods of doing a lot of tracking that are far more pervasive and probably easier to implement. The classic example being the growing concern over things like license plate trackers, which really drive me crazy because, it's crazy because on the one level you say, following someone's license plate, hey, you have to allow people to do that. But when you automate it and then save the data, you can, in effect, retroactively, you can put people under retroactive surveillance. You can say, all right, we've got a record of all the cars that were driving in this area 5 years ago. What was his car doing 5 years ago or 3 years ago or whatever? And that's like following people years after they'd done whatever they did. And I don't think that's sort of thing we should be putting up with. And that worries me. But that's a lot more likely to be a threat, I think, than the satellite passing over 3 times a day and taking pictures of your house. There could be some privacy threats there, but I'm not sure it's as direct as some of the things that are happening down here on Earth.
Okay, we can.
Of course, the downside, as I pointed out, is the people at Skybox themselves have said, we haven't thought of all the ways you could use this yet. And believe me, somebody in the NSA is thinking about it right now. So you could be right.
All right, on that, we'll turn it back over to John.
One of the things that we tried to do, and I hope you noticed, was that we weren't stovepiped into one discipline. You weren't hearing all physics talks. You weren't hearing all academics. You actually were hearing somebody who practices finding lost people for a living, and you heard a columnist or writer who studies these things, and an assortment of people, cognitive psychologists, anthropologists, astronomer. And what I'm going to try to do is see if I can make the leap into English. Okay, so we'll see if I can end up with a poet on this. This is see how I do. Okay, so one of the things that I found interesting was Robert will know this gentleman, Ken Hill, who's a researcher on lost person behavior. And as I was writing my book, I was reading one of his papers, and he did an analysis of the kind of behavior that lost people engage in when they try to get unlost. And it was rather interesting. One of them is you just try to travel in a straight line as best you can based on the premise that you're actually going to find something at the end of that straight line. And there's an apocryphal story about a hunter in Maine who was so intent on traveling in a straight line being lost that he walked right across a road and back into the deep woods. I really don't know if that's true. There's another one which is route sampling, which is you kind of go out one direction, you see if you see anything, you come back, you go out another direction, see if you see anything, and so on. Another one is do nothing. Another one that we heard is to get high and look around. And I started to think that first of all, in some respects, this is the behavior that explorers also engage in. Because if you think about Lewis and Clark, they were trying to reconnoiter an unknown area, and so they would go to one spot, and then they would basically do route sampling to try to basically do a reconnaissance of an area. Or they get to a prominent peak, and they try to do a survey and see what they're doing. So this is reflected, this kind of behavior is not just lost person behavior, but it's explorer behavior. And then, and this is kind of what's pervaded me and maybe pushed me along a little bit, is the sense that there is a bit of a metaphor about how people live their lives. So we probably all know people that pursue blindly some goal, walking over a road and going back into the deep woods, or we know people that pop around from one vocation to another, or people that just like to perch up on a high spot and survey things and kind of be Buddha-like. So I found that metaphor kind of fascinating. And Humans are a peripatetic group. We travel a lot, and so this is not a crazy analogy or metaphor. And what struck me to some extent was in Eleanor's talk was this little circle that had navigation as one circle that was touching it, but there were a lot of other aspects of cognition that were touching on the circle that goes to kind of our core of being as humans. And so this navigation is kind of a model for the way we live our lives and think about our lives is not a crazy one. I will also note that this navigation as metaphor is not uniquely mine. René Descartes coined this in one of his works called Maxims of How to Live a Resolute Life or something like that. And he said, what you should do in your life is to mimic what a lost traveler in the woods should do and travel directly in a straight line as best you can. So I don't know if that's really good advice, but the issue is that, in a sense, navigation is a tool, and then you have to have, some sense of what you want to do about it. So what I'd like to then pull it back to is someone local and suggest that there's a certain wisdom in this proto-transcendentalist poet, Ralph Waldo Emerson, who said, life is a journey, not a destination. So on that note, I'd like to end the symposium. Thank you.